Hi everyone, my name is Paulina, and today I'm modeling the spread of emerald ash borer. The emerald ash borer is an invasive forest pest that originates from Asia, and it was probably brought over in wood packing materials. It was first found in Michigan in 2002, and then first found in Vermont in 2018. It's now present within 35 states and also parts of Canada. In the upper left, you'll see a map of the distribution of the emerald ash borer, which was last updated in January of 2021, so it's fairly recent. The red dots represent locations where the insect was initially detected, and the green represents its estimated range. As you can see, it's extremely prevalent throughout the entire East Coast and has also been detected on parts of the West now. And despite how beautiful the insect truly is, it has caused hundreds of millions worth of damages throughout the nation, so much so that it's been infamously named the most destructive forest pest of North America. But what makes emerald ash borer so destructive? Well, I found this helpful graphic online to help me explain its life cycle. We know that females infest ash trees, specifically, by laying eggs, and then those hatchlings, once they grow up, they destroy the inner layer of bark, which is called the cambium, and ultimately it prevents the trees from providing sugars and resources to its roots. This causes the tree to rapidly decline in health and eventually die within 3 to 5 years after infection. And in Vermont, this is a big deal because approximately 5% of Vermont's forests are susceptible ash trees. Ash is a high-quality timber, and it is a significant source of revenue for Vermont's timber industry. But once it becomes infected, it can no longer be sold, and once infection occurs, populations are always decimated, and landowners and foresters are forced to deal with those consequences. Research has attempted to identify the best management options for infested forests. However, it's highly inconclusive, and so far the best strategy has been to take extreme preventive measures, such as thinning forest stands or removing all ash completely ahead of infection, which certainly is not ideal for people who use these trees and forests for income. Overall, there are no easy or correct decisions to make yet as the emerald ash borer continues to spread. But the inspiration for this project comes from Corinth, Vermont. A few pictures you can see here. At Corinth, we have an active logging site that's been developed in partnership with Dartmouth College and UVM's Forestry and Silviculture Lab. They're currently advancing our understanding of emerald ash borer management through scientific research. And so at this site, we have multiple high-frequency sensing networks that have been developed and installed to collect large data sets of environmental variables within several silviculture treatments that may prevent, stop, or control emerald ash borer populations ahead of infestation. So right now, it is not present at Corinth, but we do expect it to arrive in the very near future, and so we're currently trying to develop research plots, collect data, and install equipment before it arrives so that we can monitor conditions before and after its presence. So to model this system, I'm using a discrete epidemic model on a weighted network using the classic SI epidemic model as a foundation. However, instead of only having 2 state variables for susceptible and infected nodes, I've included 2 more for age groups, and that would be young versus old. My reasoning for this is that I've learned younger, thinner trees are more susceptible to infection. Therefore, I'm assuming that forests with a larger proportion of young trees will be more likely to spread the insect. In addition, distance between trees greatly influences spread. Therefore, our transmission probabilities are divided by the weight of the edges to simulate the impacts of forest density. Overall, I'll be measuring the prevalence of infected nodes by sweeping parameters over the transmission probabilities for young versus old trees. And so, for my initial conditions, as I've mentioned, I will include different transmission probabilities for young and old trees, which will be represented as beta 1 and beta 2 respectively. A death rate as well, which remains constant in this instance, And then finally, an initial fraction of infected nodes, as well as an initial fraction of young nodes. And so for this presentation's purposes, I will allow the death rate and my initial fractions of infected and young nodes to remain constant. So to begin, I made the transmission probability for young trees to be extremely high, while the transmission probabilities for old trees remained extremely low, and this is my extremes. And what I found was that infection spikes during the first few seasons after introduction, but eventually declines. This trend may be due to my death rate and the fact that all trees, regardless of age, eventually die. Therefore, once enough ash trees die, there's just no longer any trees to infest, as the emerald ash borer only infects ash trees. So next, I began to slowly decrease beta 1 while beta 2 remained low, and overall, the prevalence of infection becomes a little bit lower, but we're still seeing that same general trend of decreasing prevalence over time. And that continues as I slowly decrease beta 1. And again, we're still seeing this downward trend, but here, both transmission rates are extremely low. And interestingly, in this model, once emerald ash borer has been introduced to the system, infection always seems to prevail and take over a large proportion of the network, regardless of how different or similar beta 1 and beta 2 are. But I didn't want to stop there. I wanted to see what would happen if I raised beta 1 again, because I'm assuming that younger trees are always more susceptible. And then what would happen if I slowly began to raise beta 2, so that both populations have high chances of transmitting the infection. And what we see here is that the prevalence of infection begins to quickly increase, and populations die off at a seemingly quicker rate. And so again, I'm just increasing beta 2. But finally, when both transmission rates are extremely high at 0.98, basically as high as you can get, we see the highest prevalence of infection yet. And the trend is we're still seeing that similar downward trend over time, which I find extremely interesting. But in conclusion, I have to say that age alone is certainly not the main driver of emerald ash borer spread. Density and other environmental variables are also significant controls on this system. But sadly, once emerald ash borer, at least in my model, once it's been introduced, forests may never recover, and the prevalence of infection will proceed until the ash populations have been decimated. Which actually is what we do see in real life, which is why this insect is so problematic. Therefore, the most successful strategies still for managing its spread are to just take extreme preventive measures before it arrives. And so in future work, if I were to continue this project, I would love to create an actual network of the ash trees at Corinth, Vermont. Since I have access to this data, I think it could really bring this model to life. Thank you!